Hello, everyone, and welcome to the 8th and final webinar of Preparing for the PAT. My name is Kat. I'm the Physics Access Officer at Oxford University. And what that means is I look after all of our events for young people who are aspiring to study physics and related sciences and other physical sciences at competitive universities. I run this course on behalf of all of the departments which require the PAT as part of our admissions. So I run this on behalf of physics, my own department, but also on behalf of physics and philosophy, materials science and engineering. And later on this evening, we will be joined by my colleagues from materials science and engineering for a final Q&A session. I usually, at this point, have a presentation where I tell you what the PAT is, what the Preparing for the PAT course is. But by this point, we have all registered for the PAT. We are all ready to go. Oh, and thank you to those of you. It is the 1st of October. I am in full Halloween mode. I got distracted. So we have all registered for the PAT. We are ready to go. I have no introduction for you today, except we are joined by 3 of our particularly wonderful undergraduates who I'm fortunate enough to look after as part of my job at the university. So as well as looking after all of you, I get to look after our undergraduate ambassadors. It is great to see everyone. I have no idea which of our ambassadors is going first. I'm going to wait and see who takes their camera on, who takes their microphone mute off, and then I will share.
First, as I needed to leave by 7.
Fantastic. Akash, it is lovely to see you. Please do introduce yourself. At the moment, we can only see your name. We don't yet have your camera, but once you're ready.
Yeah, sure. So, hello everyone. My name is Akar. I'm an incoming second year physics undergraduate. I study at Corpus Christi College. And Kat, is it possible to give me like a few minutes to start my video? Just a second.
Yeah, absolutely.
Yeah,
Ah,
this is
there
just
we are.
from my laptop because like I'm on my iPad. I'll be sharing it from there.
Good to see you. Well, at least we know Akash is there, everyone.
Just a second. Yeah, I'm joining in from my laptop.
Yeah, all good. Don't worry, we always have these tech issues. Well, not even an issue. It always just takes time to get tech up and running with as many of these problems and problem solving sites and chats and everything that we want to have ready. What I'm going to do while Akash is getting all of that set up is I'm just going to share the problems in the chat. It's lovely to see you all wishing each other good luck as well. We'll make sure there's plenty of time for that at the end. It's lovely to see so many familiar names as well. Great to see everyone. Okay, so the problem set for today, Akash, I have shared your problem set for you in the chat. So just in case anyone missed it in the email, it is right there.
Yep. Okay. So I hope you can see me now.
Yep, all good.
All
I
right.
will head into the background in that case, Akash. I'll be answering any questions and keeping an eye on the chat if you need me.
All right. So I'll start sharing now. Okay, I hope you guys can see my screen. So I'll be taking the last 2 questions of the problem sheet, questions 7 and 8, while the others will be taken by my colleagues. So I hope you guys can see the question I have over here. Just a second. So this is question 7, which says, imagine that a tunnel is constructed straight to the center of the Earth. If a person were to fall into the tunnel, would they arrive at the other end? Describe the motion of the person and either explain why the person would not reach or calculate the time taken for the person to travel. So, what exactly this question wants us to do is we have a scenario quite like this, where we have a person which I'm approximating to be a small point mass, and it's going to fall from this end of the Earth, and somehow we have constructed a tunnel to the other end. And we want to know whether it will fall to the other end, uh, or will it get stuck in the middle or just come back, bounce off, whatever. We don't know for now. So a few guesses could be that, like, oh, if it starts from here, it'll keep going. It'll keep going till the center, and then as you might know, there is no force at the center of a sphere. It might just stop or just like keep going till on there and then might turn back. We don't know for sure. So we'll try to find that out and see what happens. So to analyze this properly, we'll need to know what the gravitational field inside of the Earth would be. So for this, we'll use Gauss's law, which states in a spherically symmetric case that the mass outside the radial distance at which the object is at produces no force. So if we have an object inside a sphere, suppose it's at a certain distance, all this mass outside that distance, it has no contribution on the force acting on it. So like even if there's a lot of mass outside or no mass outside, that'll have no effect on the gravitational field at this point mass. So with that out of the way, the second thing that we need to know that the mass inside the radial distance at which the object is at produces the same force as if the entire mass was at the center. So if we have the same object situated on top of a planet, the gravitational force at this mass would be equivalent to the case in which this entire planet is concentrated at its center. So we can just use the simple formula of Newton's gravitational law, G m1 m2 over r squared, to calculate the force between the two. We do not have to do any messy spherical integrals or any of that for a sphere, which our Earth is. So let's start solving the question, and we'll assume that the object is currently at a radial distance r from the center. And to calculate the gravitational field, as I said earlier, we need to only concentrate on the mass inside that radial distance. So what we'll do is first find out the density of the object, which would be its total mass, which is the mass of the Earth, divided by the total volume of the Earth. As the Earth is a sphere, we'll have 4 by 3 pi r cubed. Total mass over volume, this is the density. And we'll multiply this by the volume we are concentrating on, which is just the volume till the radius r. So that's just 4 by 3 pi r cubed, because that's also just a cube, a sphere. So on solving this, cancel out 4 by 3 pi r. We get small r cubed upon capital R cubed. And as we know, as we discussed earlier, that the force applied by this mass that is inside that radial distance is the same as if it all were concentrated at the center. So that's just gm1 m2 over r squared, directed inwards. The direction is also really important. So what we have is minus g, that mass that we calculated earlier, times small m. Small m is the mass of the object that we're concentrating on, upon r squared, which is the distance between the center and the object currently. And the negative sign is important because the force is directed inwards, as in like r increases outwards, but the force is directed inwards. So that's why the minus is there. Simplifying this, we cancel the r squared with the r over here, and we get minus gmm r over r cubed. So now we just have to use Newton's second law of motion, which is mass times acceleration is equals to the force. So here our coordinate that we are using to measure distance is r, which is the radius from the center of the Earth. So we'll just have the second derivative of that. So we've got mass times acceleration equals the force. And if we take the small m to the other side by canceling it with this, we get acceleration is equals to negative gm over r cubed times the distance, which is r, which is something very familiar. This is something you should have noticed by now, that the acceleration is proportional to the negative of the distance. This is when we have simple harmonic motion. So now that we have identified that it's simple harmonic motion, it's pretty easy from now. We know that the angular frequency is just the square root of this quantity in the brackets. So that's square root of gm over r cubed. And then we need as we need to find a time period in the question, it will be useful to find out the total time period of the motion. That would be just 2 pi over omega, because frequency is equals to omega over 2 pi, and time period is 1 over frequency. So if we just rearrange those formulas a bit, we'll get the formula for the time period, which would be 2 pi times the square root of r cubed over gm. When we put in the values for these in a calculator, I will not do that right now because that's messy, we get approximately 85 minutes. But in the question, it was asked that we need to describe the motion that we have done. It's a simple harmonic motion. And then we need to tell whether the person would reach the other end or not. So we know that the person started from one end. So if you have a pendulum that starts from, let's just say, 10-degree angle, and if you leave it, it always, assuming there is no air resistance and all of that, will always go the other 10 degrees. Like it will not stop at 8 degrees, because that means some energy has been lost, which we are ignoring, and it will never go till like 12 degrees or something, because that means that you've got extra energy in the system, which is just violation of energy conservation. So we always know that, like, if we start at a certain point, which is the amplitude, we'll always end at the same thing on the other side. So yes, it will reach the other side. And to calculate the time for it, we know that this is just half of the oscillation. A full oscillation would be going from this end to the other end and then coming back. That's a full oscillation. But we only care about half of it, so we'll just divide it by 2. So the time to complete one oscillation is this 85 minutes, but we only need half of it. So that's just 85 over 2, 42.5 minutes. So we have the answer for this one. Do we have any questions?
We've had one person, in fact, we've had two people suggest alternate methods, which is quite
Oh,
interesting. So in the Q&A, we've had somebody say, would the working for this question be similar to a question about rotation of a galaxy and the acceleration of the edges? And we've had somebody ask if you could do it using SUVAT as well. So those are both really interesting equations.
oh, that's really exciting. So first, I'll
Yeah.
answer the first one about dark matter and all of that. Yes, that is very correct, and like that's a nice observation, I'd say. So
Yeah,
if
I
you have
thought
a
so too. I like that.
so if we have a galaxy, we would also use the same Gauss's law to calculate the force and thus the gravitational field. And using the gravitational field, we can also find out the velocity. And when we actually do that, we find out the velocities are higher than what we expect, which means that there's supposed to be more mass in the galaxies than we can see. So that's where dark matter comes in. So yes, that's a correct observation. The other
Love
thing that
it.
someone mentioned is, could this question be done using SUAT as well?
Yeah.
Yes. And the issue is that SUAT, we usually have it for constant acceleration, but in this case, as you can see, the acceleration is variable. So you'd have to modify it essentially. So like you won't have like ut equals half eight. Sorry, s equals ut equals half at squared, because the acceleration here would be variable acceleration, not constant, for which this formula is derived for. So we need to do it using equations of simple harmonic motion and not SUAT. So they are not particularly valid here. But like the same concept goes, like these equations of SUAT are derived from integrating a constant acceleration motion. The equations of SHM are derived from integrating an acceleration which is dependent on the distance.
Lovely, thank you. We've got a few questions, but I
Yeah.
think what we should do is why don't you present the next one and potentially Eugenia and Maisie might be able to answer one of those in the chat. And I'll have a look and see which ones I can answer as well. I just realised it
Okay.
doesn't need to be you
I'll
guys.
just answer
I can always do
one
my
of
own
them.
physics.
I'll just answer one of them, which is like, how did you get to the equation of omega?
That would be
So
really helpful, thank you,
this,
because that's harder to type out.
yep. So this that we have here is the equation of motion. So then you need to like essentially map it out to the general equation of the SHM which we have, which is just d2x over dt squared equals minus omega squared times x. So when you map these two together, you can see that like, oh, this corresponds to this corresponds to this, and thus omega squared corresponds to this. So that's how you get to omega from this equation. And the other thing is, can this be done in terms of energy conservation? Yes, you can do that. You'll get to the same equations. You'll just write energy equals kinetic energy plus potential energy, and if you differentiate it with respect to r, you'll get to the same equations. So yes, you can do that. uh Yeah, I think that's all the questions. So I'll go on to the next one. Is that all right?
That's great. I'm going to answer the kind of ones about the pat and difficulties and stuff in the
Okay.
background. Thanks, Akash.
Okay, fair. Yeah, so we'll move on to the next question. So this one is about projectile motion, kind of, but yeah, let's just read the question first. In the A Team film, Hannibal and his team find themselves plummeting towards the Earth in a tank with only one of its parachutes attached. This would not be a soft landing. However, there is a lake half a mile, we'll underline that, away from the landing spot. The team attempt to fly the tank to the lake by firing shells horizontally. This question will examine whether this is pure Hollywood or based in sound physics. For the team to be successful, how high up they must be when they execute this plan. You may ignore the effects of resistance in the horizontal direction. So we've got the mass of the projectile, the velocity at which they release the projectile, which is muzzle velocity. We've got time between the shots. We've got tank mass, terminal velocity, all of that. So because what we have here is we've got something they call a tank, and they are shooting out these small projectiles out of that. So because you're essentially throwing them out, you're applying a force, and because you're applying a force, it will apply a force backwards on you, and thus you'll essentially recoil. This is just, if you fire a gun, you get a recoil. This is the same concept here. So we need to find essentially the force due to this shooting, which is change in momentum that we impart to these shells, divided by the change in time. So that's just the mass that we are firing per unit time times their velocity and times the time between each of them. This is essentially an average force. In the actual, more exact case, this would be like you'll get a large force and then it'll drop down to zero and then another after 3.5 seconds and all that. But we can approximate that because the time period is small between the two shots. So if we do that, we get a force of 5,000 newtons. And now we'll make a crucial assumption, which will simplify the problem a lot. And we also need to just like see if this can roughly happen, or we don't need to be really exact. We'll assume that the changing mass of the tank, which happens due to the firing, is negligible, and we can ignore that. We can like assume the mass of the tank to be constant. So the acceleration of the tank, which would be constant because this force is constant, would be just A equals F over M, which is 5,000 upon the mass given, just 5 or 22 meters per second squared. And this is a constant acceleration. So there's no like weird integrals that we have to do. So we can just use the Suvat equations. We'll also assume that the initial horizontal velocity is zero. So they're just like falling straight down, and then they start shooting the shells, and then they get an acceleration. So they kind of do something like this and they fall into the lake. So we've got the distance to the lake as 800 meters equals half AT squared, so half AT squared. Solving this, we get T equals 84 seconds. And we just need, yeah, so this is like whenever they start, and if they are successful, it'll take 84 seconds for them to like reach the lake. So we need to see like what height they will fall during this process. So we've got H equals VT. They've given the terminal velocity of this falling tank. Terminal velocity essentially means that because of the air resistance, the force of the gravity and the air resistance, it has balance, so it does not accelerate anymore. So it just like falls at a constant velocity downwards. So we've got the height that it falls during this time that it takes to reach the lake is V times T. So this 14.75, that's 33 miles per hour in meters per second, multiplied by the time in seconds, you get 1240 meters. This is like about a kilometer. So if they are at least about this high, they will make it if they start shooting these shells. So like it's not completely unrealistic, it can happen. And now we'll just validate our assumptions that we initially took and see if they are valid or not. So we said that we'll ignore the mass change. So we'll just calculate the mass change and see if it is ignorable or not. So we can calculate the number of shells fired as 84 upon 3.5. That's like the total time and the time between each shell, between each shell. So when we do that, we get about 24 shells, and then we can find the mass of 24 shells, which is 240 kilograms, which is fairly less than our original tank mass. So we can ignore it. It's not very ignorable, but like it's fine for the sake of an estimate question. So that's all right. So we are justified in ignoring it. So yes, it is possible, and we are justified in assumptions. So we have solved the question. So do we have any doubts in this? I don't see any. Is that all right?
Yeah, I think think so. I'm answering a lot of questions about splitting up a lot of questions about whether long questions like this would still occur on the PAT. That was hard to say. I'll switch my video on. I'm answering lots of questions about whether or not this is still relevant to our current PAT format. So just to say for everyone, absolutely. Our new PAT is really similar in style to the old PAT. So just imagine this, but with each of these stages of working themselves being a multiple choice question, basically so that we can still check your working as we go, even though we don't receive your written working. So really relevant, and yes, there will still be questions like this. Thank you for
Someone has
scrolling
asked
up,
about how did you
Ask.
get S equals half AT squared? So that's just SUVAT. So we have S equals UT plus half AT squared. So we know, as I said, we're assuming that initially they are just falling straight down and then we start firing. So their initial horizontal velocity is zero. Also, like this is in the horizontal direction. This is SUVAT in the horizontal direction. So in the horizontal direction, their horizontal velocity before firing is zero. So U is zero. So we just get S equals half AT squared. I hope that clarifies.
Yeah, looks good. Thank you.
All right.
Now, are those your last two questions, Akash?
Yeah, I'm done. The rest are with Macy and Eugenia. Yeah.
Thank you so much for joining us. It's been great to see you. I know you're shooting straight off to another webinar as well,
Yeah.
so thank you very much.
All right. Thank you.
It was
See you guys.
lovely to see you.
Best of luck for exams.
And who have we got next? Eugenia or Maisie? Who's going next?
I can go first. We haven't.
Hey, Maisie, good to see you.
Hello, hi everyone. Just to introduce myself, I'm Maisie. I'm going into my third year studying physics at St Peter's College. I'm going to be doing questions 1 to 3. Just got to get it.
Yeah. It always takes a minute for us all to sort out all of our various screen shares.
Okay. Hopefully, can you see my like mirror board?
Yeah, I think we're all good.
Okay. Oh, doesn't want to zoom in.
Once you're all set, I'll switch off and head into the background again.
Oh. My Wi-Fi may be struggling a little bit.
We'll make it work, don't you worry. You got me and Eugenia to back you up if anything goes terribly wrong, don't worry.
Let me stop the shower and start again.
Yeah, we did have a nice plain green screen there. So what I will do is there's a couple of questions, things like, will all of this working be uploaded? We're not going to be uploading the paper copies, but after tonight's webinar, I am going to upload a complete set of solutions for all of the problems we have done over the last 8 webinars, and all the recordings will be available as well. So not this particular set, but I will be uploading a complete set of solutions. So hopefully that will help. I will say as well, for almost everyone who's asking, could I do it this way? If your physics is correct, yes. So we are much more interested in your physics. What we are presenting at any time is only our own way that we would solve something. Has that bought you enough time to get your screen sorted out, Maisie?
I think so.
Excellent.
Okay, brilliant. So yeah, let's start with question 1. So we've got a smooth marble is initially at rest at the top of a much larger smooth hemisphere of radius r. The marble is given a slight nudge and begins to slide down the hemisphere. So question A is, at what angle from vertical will the marble leave the surface of the hemisphere? So first thing in physics, always draw a lovely diagram. It's not a very lovely diagram, but it'll do. There's my marble on my hemisphere, and it's got a radius of r. So I'm just going to mark that so I remember. And we're looking for an angle from the vertical where it's going to leave the surface. So if I kind of sketch maybe the marble just as it's about to leave the surface, I can label that angle. I don't know what it is yet, but I'll just call it theta. So the angle theta is when I think it's going to leave the surface. So good thing to do here is, you know that when something leaves the surface, that's when the normal reaction force is 0. So I'm going to try and resolve the forces so I can find some equation involving normal reaction force and then set that to 0. So forces acting on this marble, let's do it in a different colour, are going to be gravity. And the normal reaction force, which I'll label R, which acts perpendicular to the surface. Yeah, that's all the forces because it's a smooth marble, so there's no friction we need to worry about in this case. We also know that, so if we resolve them kind of in this direction, we can resolve the weight like this, and that angle's theta. So the centripetal direction of the weight will be mg cosine of theta. So then if I put that all together, in circular motion, you should know that the acceleration can be written as v squared over r. So just using F equals ma, but substituting that circular motion acceleration in, we get, so the forces are going inwards is mg cos theta, going outwards in the opposite direction is r, so that's minus r, equals m v squared over r. We can set that r to 0 because we know at theta that's when it's leaving the surface, so there's no reaction force. So we have, cancelling the m's, we have g cos theta equals v squared over r. Unfortunately, this is not quite enough information to solve the problem yet. So let's think about what other kind of things we can use. And a good one to default to in physics is the conservation of energy, which in this case is the right one to use. So let's consider the energy of the marble at the top of the sphere. So at the top, the total energy is, we've got 0 kinetic energy because that's just when it's stationary, or just after it's been nudged, we can say there's no speed. And the gravitational potential energy, I'll just measure it sort of from the bottom of the hemisphere, is going to be mgr. So that's mgh, but the height above the surface is r. Okay, and then at theta, the energy is, well, it's got some kinetic energy because it's rolling, half mv squared, and height is different. So how do we find this height? I might just draw another diagram here because this is getting a little bit cluttered on my main diagram. Oh, it doesn't want to zoom, that's okay. Okay, so it's going to look a bit like that, that's the theta. That's the r, that's where the marble is. And if we want to find this height, hopefully you can see from that diagram that this triangle gives us the height as being r cos theta. So it's mg r cos theta is the gravitational potential energy when the marble's at theta. And then by conservation of energy, let me scroll down a little bit. By cons of energy, you can equate them. So it's mgr equals a half mv squared plus mgr cos theta. Let's do a bit of cancelling and rearranging. So cancel the m's, and then we can put the grs on the same side. So we're going to get gr 1 minus cosine of theta, and I'll bring that 2 over from the half is v squared. So we get that v squared is 2gr brackets 1 minus cos theta. And then that's nice because in our equation up here, that's got a v squared in, so we can just sub that straight in to give us g cos theta equals 2g, well, it's r over r, so they're going to cancel, 1 minus cos theta. Okay, and our g's are going to cancel, so we get cos theta equals 2 minus 2 cos theta, and this is looking very lovely, 3 cos theta equals 2. So cos theta is 2/3, so theta is according to my calculator, about 43 degrees. So the angle that the marble loses contact from the hemisphere is at about 43 degrees from the vertical. Hope that's all right. If there are any burning questions, Kat, you can interrupt me, but otherwise I'll just keep going on to part B.
I think we're okay. We had a question about why we don't take R as 0, but I think Eugia is typing in. And somebody has said, how did you get from v squared to the next bit? So I think just missing that step.
Here.
Yeah, I think so.
I so, yeah. So
they can come back to us if not.
Yeah. So what I've done is I've taken this equation up here that I've just circled, which we got from resolving the forces, and I've substituted our new equation in, so that g cos theta on the left is from the upper equation. Hopefully you can see that, and it should be technically that. The r's have cancelled as well. So that's come from combining the forces equation and the energy equation, but I didn't write that down very clearly. Okay, so part B was, how far away from the base will the marble land? This is a fun one. There's a lot of algebra coming up. Okay, get excited everyone. So let's think about it for a second. After leaving the hemisphere, what do we think is gonna happen? It's good to sometimes like take a step back before you go and do loads of maths that you're not entirely sure is correct. Take a step back and think about the physics of what's actually happening. So there's a marble and it's rolling and it's got some speed and it's leaving a hemisphere. So hopefully it should be pretty obvious that that marble's gonna fly along and then hit the ground. And the forces acting on that marble while it's in the air are, we'll just assume, just gravity. Don't need to worry about air resistance or anything. So actually this becomes quite a nice projectiles question. It's just got a little bit of extra stuff at the start. So if we think about when the marble's leaving the hemisphere, it's got some kind of speed, and in circular motion the speed always acts sort of perpendicular to the radius. So the speed looks like that. And we also have an equation for the speed from before, from when I used conservation of energy and the forces as well, which was 2gr 1 minus cos theta equals v squared. I know that at this angle where it's leaving, and so sort of the initial speed we're going to be using, we know that cos theta is 2/3. You could use that theta is 43 degrees and then put that into cos, but it's a little bit easier just to keep it as that nice fraction. So cos theta is 2/3, so that means we end up with, if you substitute that in, 2/3 gr equals v squared. So v is 2gr over 3, all square rooted, and that's the initial velocity in our sort of projectiles. So I might actually just change that to a u, because that's what we usually use for initial velocity. Okay, so we've got a projectiles question. We've now been given the initial velocity. All we need to do is to split it into its horizontal and vertical components. So if I kind of resolve this u, you end up with theta here. So the horizontal initial velocity is u cos theta, and the vertical velocity, which I'll label with, I've done x and y, x for horizontal, y for vertical, is u sine theta. Okay, so then what I like to do is sort of smooth out questions is to make a lovely table of all of my values that I have. So I'll do the vertical component and the horizontal component, and then s, u, v, a, t. Might not need all of these, but it's good just to write them down. So I'll put my u in, because I know that one. That's u sine theta for vertical and u cos theta for horizontal. Acceleration, for vertical direction, it's going to be gravity. So I've decided that, I've probably decided this actually. I'm going to decide that downwards is positive. You could also do this whole question with downwards is negative and upwards is positive, which is how you often do it, but just because we're starting off going downwards and gravity's going downwards, I'm just going to use the downwards is positive as my convention. I like to kind of write that down so I remember later on. So acceleration is going to be g, downwards. We don't need to give it a negative sign in this case because I've defined positive as downwards. There's no acceleration in the horizontal direction, so that means that the final speed is also going to be u cos theta. And then I don't know any of the other values yet. So if I want to find the distance this marble travels after it leaves, the first thing to do is to find the time it takes to reach the ground using the vertical Suvat equations, and then from that time I can substitute it into horizontal equations to get the distance it's travelled in that time. So let's first look at in the vertical direction, finding the time it takes to reach the ground. Oh, there's one more thing that we have in our Suvat table that I haven't put in yet, and that is this distance from the marble's initial position to hitting the ground, which we already know is r cos theta. This is the same one as when we were working out the gravitational potential energy at theta, so that's r cos theta. Okay, so I have s, I have u, I have a, and I need t, so the Suvat equation using all of them is going to be s equals ut plus half a t squared. So then if I substitute them all in, r cos theta equals u sine theta t minus plus half g t squared. That's the equation we get. And then we'll substitute all of these values in. I'm not going to do all of the algebra because it's going to take a really long time, and also I don't want to mess it up in front of everyone doing this live. Oh, just one more thing for when you're substituting in. We have cos theta is 2/3, and to find sine theta, you could substitute in that 43 degrees, but to make the algebra a little bit nicer, you can use Pythagoras. Not Pythagoras. Well, you could use Pythagoras, but you can also use the 1 equals cos squared theta plus sine squared theta. So 1 is 4/9 plus whatever sine squared theta is, and of course sine squared theta is going to be 5/9, so that means that sine theta is √5/3. So yeah, we have cos theta, we have sine theta, and we have g. You just have to leave it in terms of r, and you can leave it in terms of g as well. And you have a kind of ugly quadratic equation to solve for t, which if you use the quadratic formula, you end up with this very, very lovely expression. Square root of 2r over 27g, all multiplied by minus √5 plus or minus √23. So you can hopefully see why I didn't want to do that live. For time, because it's a real thing, we take the positive value, we take the positive root, because you can't have negative time. So that's our answer for time. So then we need to find the horizontal distance that the marble has travelled in this time, and you can do that just using distance equals speed times time, because there's no acceleration in the horizontal direction. So distance equals time multiplied by speed, and if you sub that in, the distance is 4r over 27 times √23 minus √5. Another lovely answer. But wait, hang on. This isn't quite the final answer. It might be easy to kind of think it is, because we have a horizontal distance that the marble has travelled. But if we look carefully at the wording of the question, it says, let me find it, how far away from, how far away from, sorry, I confused myself, how far away from the base will the marble land? So we've actually worked out the distance from this point, from theta, that the marble has landed. But there's this cheeky distance here, which has been, it's there to trip us up. So we need to subtract that from our distance. So, I've lost my answer. Okay, so the actual distance is going to be that distance there, sx, minus r sine theta. And we know sine theta from earlier, it's √5/3. And so if you substitute them in, you end up with approximately 0.125 r. So that's the distance that the marble travels from the base, so the edge of the hemisphere, to when it hits the ground after it leaves the hemisphere. Yes, okay. So I'll pause there to have a look at any questions. Where is the questions?
I think my favourite question, Maisie, which I answered quickly and just want you to know that somebody asked, was, are you giving a good example of how to answer these questions in interview?
I
said,
so.
Yeah, no, I said straight away, I was like, yes, because not only is Maisie showing how to keep problem solving out loud, she's showing you how to keep up a good problem solving pace as she does it, which is like the holy grail of this. Can you do it out loud and can you still get through all of the problems? So very
That's
well
something
done.
like, I don't know how many of you on here have tried it, because it's something I never really thought about before I sort of, probably was your age exactly when I was thinking about the PAT and doing maybe interviews, was like explaining your working out loud, because for me and for most people it is so much easier just to write it down
Yeah.
than to explain it. Well, that's probably just because like you're never taught to explain things out loud when you're, especially complicated things like this. So this is good practice for me as well, honestly.
It's good practice for all of us whenever we do it, isn't it? We have had somebody who's asked, could you just explain that last step about measuring from the base?
Yeah, it would probably be good if I drew another diagram. Or actually, I can just go back to my original diagram.
And I think that might cover in, 'cause somebody else has asked, why are you using r cos theta for vertical? And can you explain where the r sine theta comes from? So I think you're about to take in both of those.
Yeah, so the r cos theta for the vertical is, gosh, there's a lot of triangles happening here. Oh no. Is like this triangle. So there you go, I'll do it here. That's the r, that's the theta. So if we want this one, you're going to use cos because it's the adjacent side. And then my sine theta has come from oh gosh, my diagram's confusing me. There's too many things happening. Okay, so let me take it to the side a little bit. I sometimes find it really hard to visualize which angles are happening where, so I find just like drawing loads and loads of triangles and labeling loads of angles is kind of how I get around that. So I'm going to do it like this. So that's the right angle. Then this one also must be theta. And if we want to find this distance, this is the distance between where the marble leaves the hemisphere and the edge of the hemisphere. Then this is going to be, this is going to be theta. So then we're going to use the sine theta for that. Hopefully that's clear.
Yeah, all good. Thank you. Lovely. And you even got a few little hearts coming through as well. So I think you're good. And we've got one question about the quadratic equation, but I think that question is just so it's how do you remove u from the quadratic equation? And I think, is that just when you said it was equal to 0?
Oh, is it here?
Yeah.
Yes. Yeah.
Yeah.
Let me find it here. Where's it gone? Here, so you can use the u that we just found, which was up here. That u is root 2gr over 3.
Perfect, thank you. I find with this I can keep up with, I can either problem solve or answer questions about the PAT. I can't do both at the same time, which is why you are all here to help with that. Is that your final question, Maisie?
No, I have 2 others.
Oh, okay. In that case, we are going to go a little bit quicker on these next ones. So anything, that's my fault, not yours. Anything that you're not sure about, do bear in mind. I'm going to share solutions and you'll be able to rewatch these videos as well. But we'll do our best to answer in the chats, in the Q&A as well.
Yeah, my next 2 are much less algebraically heavy.
Perfect, thank you.
Thankfully. So I will look at question 2 next. Okay, so question 2. Consider a toy car going around a loop-the-loop. If the car is going too slowly around the loop-the-loop, at some point it will fall off. So question A is, if the car started at rest on a downwards ramp which was initially at the same height of the loop, So as you can see in the diagram, would the car make it around safely? Explain why. So just by sort of conservation of energy, you can see that here, when the car is at the top of the ramp, it has, well, it's starting at rest here, so it has 0 kinetic energy, and it has whatever this is, height, gravitational potential energy, and then if it gets back to this same height, by the conservation of energy, it must also have no speed here. It must have no kinetic energy when it gets to this top of the loop, which means that not only is the car going slowly, but it has stopped. So as explained in the question, if the car's going too slowly, it will fall off. I think we can probably assume it would fall off here. So the explanation is by conservation of energy, the car would have, oh, let me make that a bit smaller. The car would have 0 kinetic energy at the top, so would fall off. Okay, part B. So Bob wants to find out if it's possible to do the loop with a real car. He has built a loop which has a 6-meter radius, and his car will approach the loop driving on a flat runway. Go Bob. What is the minimum speed in miles per hour that Bob needs to drive at in order to perform the loop successfully? So, to find the condition to not fall off, let's consider what's happening at the top, because the top is sort of the most extreme point of the loop. That's when, you know, best case scenario, that's when you're going to fall off, if at any time. So I'm going to look at the forces acting on the car right at the top. So what forces we've got? We've got the weight of the car, and we've also got the normal reaction force, which, well, it's also acting vertically down, but let me draw it in a different colour. Got the normal reaction force, and it's obviously got some centripetal acceleration. So we consider the forces at the top. That's going to be that mg plus r equals mv squared over r. That's using the acceleration as v squared over r for circular motion, which I used in the last question. And so the absolute limit of this, or kind of the worst case scenario, is that it only just manages to stay in contact. So we'll use the limiting case of when normal reaction force r goes to 0. So that means that we have the equation g equals v squared over r. That's me just cancelling out the m's. So that means that the kind of limiting velocity is root gr. So we need to find the minimum speed that Bob needs to drive at. So that's the speed that Bob needs to drive at on his approaching runway. So we can do that using conservation of energy. So if we consider Bob's speed just as he's entering the loop, so right at the end of his runway and right at the beginning, or right at the bottom of the loop, the energy is going to be a half mv, let's call it just v0 squared, kind of is this some speed that we don't know, and he's going to have no potential energy, so that's a 0. And then at the top of the loop, the energy is going to be, well, we know the limiting velocity, so that's going to be a half mv, I'll just leave it there, v lim squared plus, and it is going to have some gravitational potential energy. The height is going to be, if that's the radius of the loop, then the height is going to be 2 radii, so it's going to be mg times 2r. And then by conservation of energy, we can equate those equations, so we get a half mv0 squared is equal to a half mv lim squared plus mg times 2r. Multiplying by 2 and getting rid of the m's, you get v0 squared equals v lim squared plus 4gr. And then we know v lim from above, that was, was the square root of gr, so I'll sub that in. v0 squared equals gr plus 4gr, which equals 5gr. And so V0 is root 5 GR. And that's the minimum speed that, what's his name? Bob? Yeah, Bob needs to drive at, needs to enter the loop with in order to get all the way around. The question gives you some numbers. So if you substitute in the radius is 6 and G for 9.81, you should end up with about 17 meters per second, which is about 38 miles per hour. And then part C is there any reason why Bob shouldn't go much faster than this minimum speed? Okay, so that's his minimum speed, and the question's saying, you know, why wouldn't he just go really, really fast? And this is one of those ones that they like to kind of tack on the end of a physics question to check you actually know what's going on in real life. One answer you could have, which I think is kind of the main one, if he's going too fast, he might pass out due to the large G-force acting on him. Like if you're on a roller coaster and then the roller coaster will malfunction, you're going really, really, really fast, you probably pass out, or the roller coaster will break. Hopefully not. Due to the large G-force, which we wouldn't want that to happen for Bob. Yeah, okay, so that is question 2. A little bit shorter than the last one. Are there any questions?
No, you're good. You had a few people saying that was beautifully presented, so I'd take it, run with it, go to the next one before the questions come in.
They're kind. Okay. Question 3. Let me just move this along a little bit so we've got a bit more space. Okay. Question 3. A velodrome allows cyclists to travel at high speed around tight corners since the track is banked at a steep angle. So part A. By drawing a force diagram, show why this banking is necessary. Determine an expression for the maximum. Determine an expression for the maximum speed a cyclist can travel at as a function of the radius r of the corner and the coefficient of dynamic friction mu. Okay, so the banking is necessary because the cyclists are going really, really fast. Not entirely sure how the diagram shows us, to be completely honest, but I'll just draw the diagram with the forces acting because we need it later anyway. So you've got weight acting downwards, you've got a normal reaction force acting that way, and you've got a frictional force acting down the slope. So the banking means that because the cyclists are going so fast, they don't slip off. So if you had a normal flat track, like an athletic running track, and the cyclists are going really, really fast, they wouldn't have that extra help of the slope to keep them on the track. So the banking allows them to go fast without falling off the track, basically. And then the next thing is we need to find an expression for the maximum speed of the cyclist. So the question's already helped us draw the force diagram, so a good thing to do is to resolve these forces. So I've added in my angle theta there to kind of label the slope of the slope. The angle that the slope is at to the horizontal. Okay, so let's do that now, and I'm going to resolve it in terms of horizontal and vertical because we've been given the radius there. So force is going to look like that, and that's going to have theta there. And the normal reaction force is going to look like that, and that's going to have theta at the top. And weight is already acting vertically. So in the horizontal direction, we've got that centripetal acceleration because it's circular motion. So we have mv squared over r for our ma, and then the forces are going to be f, that's going to be f cosine of theta, f cos theta, plus r sine theta. In the vertical direction, there's no acceleration because we're assuming they kind of stay at the same level on the track. They're not kind of moving upwards or downwards because of the friction. So we have 0, a is 0, is acting upwards, r cos theta.
Okay, I found this on the web for is. Check it out.
I don't know if you can hear that. I just woke my Siri up. Thank you, Siri. She's obviously very enthusiastic about physics. Don't even know what I said to encourage Siri. That really scares me. Okay.
That was very funny. Don't worry about it.
I thought it was you, and then I was like, it doesn't sound like Cat, that voice. Okay.
No, not me.
Okay, so vertical forces. What vertical forces we got? We've got R cos theta, and then acting in the sort of opposite direction is F sine theta, and also mg. So we're looking for the maximum speed. So friction, the maximum friction, the equation for that is just mu times r. So we can substitute that in as well to give us, I might just put them all, separate the sides to make the negatives go away. So we have r cos theta is equal to mu r sine theta plus mg. And also the horizontal one will become mv squared over r equals mu r plus r sine theta. So we're looking for, what are we looking for? We're looking for the speed in terms of, in the question it says in terms of r and mu. Notice there's no big R, there's no reaction force that they're looking for in the question. So best thing to do is to sort of combine these equations to eliminate the reaction force R. So if you kind of rearrange them, you get that the horizontal one becomes R equals mv squared over r times 1 over sine theta plus mu cos theta. I'm skipping the algebra for time and again for my sanity. Feeling a little bit shaken after I was interrupted by Siri. And then if you use the vertical equation, is going to give us that r is mg over cos theta minus mu sine theta. So you can set them equal to each other, so then the r will go away. Mv squared over r times 1 over sine theta plus mu cos theta is equal to mg over cos theta minus mu sine theta. And then if we rearrange this all to make v squared the subject, we end up with v squared equals gr times sine theta plus mu cos theta over cos theta minus mu sine theta. And so the maximum speed that the cyclist will travel is the square root of all of this, which I've realised I didn't need to write out all over again, but I am now. Cos theta minus mu sine theta. So that is our maximum speed. Okay. Ooh, lots of algebra. Part B, less algebra. Well, same amount of algebra, but I don't need to do it. Part B is determine the value of mu required for a bike to travel at 80 kilometers an hour around the corners of radius 25 meters with a maximum banking angle of 42 degrees. So they've given us a speed, a radius, an angle, and they want us to find mu. So if we look at our equation from before, we've already got all of those. We've got an equation involving all of those things, so we don't need to do any new physics. We just need to do some maths. We need to rearrange this lovely equation to make mu the subject. So I'll just do a few of the steps. So you end up with v squared equals gr sine theta plus mu cos theta over cos theta minus mu sine theta. And then algebra, you end up with mu equals v squared cos theta minus gr sine theta over v squared sine theta plus gr. I've written sine theta in my solution, but it should be cos theta plus gr cos theta. So then you will substitute in the values you've got. So that's 80 kilometers an hour, which is about 22.2 meters per second. We've got theta is 42 degrees, r is 25 meters, and g is 9.81 meters per second squared. So if you substitute them into your equation, you get that mu is 0.40 to two significant figures. And it doesn't have a unit because it's a coefficient, it's just kind of a ratio. Okay, any questions for me? Did we find them? Someone asked, would G-force be the same as the normal contact force? I assume that was relating to this question. Let me have a look at what that means. Would G-force be the same as normal contact force? Do you mean okay?
Yeah, I wasn't quite sure. I think that was actually quite far back. I think it might have been when you were talking about Bob.
Oh, like Bob.
Like that bit at the end.
Experiencing the G-force.
Yeah, that's why I hadn't answered. I think it was quite a while ago.
Yeah. I don't entirely know what G-force is. I think it's just like the force your body experiences, like when you're going really, really fast.
Yeah, like it's multiples of gravity.
It's multiple. Yeah, it's called G-force. So it's not actually like specifically from gravity. It's called G-force because they say like you might experience like 3G, which is like 3 times the force of gravity.
Yeah.
So
yeah, that's how I understand it.
You probably could like from forces and stuff, but it's yeah.
Yeah, I think we're good. Do come back to us, Aaron, if we didn't get that. We'll try to type it up. And then we had a question on your algebra. I think just because we do need to move on, I might call it. We'll see what we can type up in the chat. Questions about different methods and about the algebra, I would say just have a go at working through it. Take a look at the solutions when I post them as well and see if you can go through those together. But you should be all right once we come through. And does that mean we are switching presenter? Are we over to Eugenia?
I think so.
Amazing. Eugenia, who's been doing sterling work behind the scenes, answering loads of these questions by type as well, so that we've been able to divide them between us. Maisie, lovely to see you. I know you're heading back to Oxford. So for those of you who need a bit of context, we start our terms very late in Oxford, which means that our students still aren't back. And in fact, term doesn't start officially until the 12th of October.
Yeah, I think so.
We've got quite a while. So all of our undergraduates who've been joining us over the last couple of sessions have been joining in the middle of their break. So an especial thank you for getting back into your problem solving head, even though you will have been doing work over the summer. But please go enjoy the rest of your evening. Feel free to switch off. Eugenia and I will take it from here. And then in about 10 or 15 minutes, we'll be joined by our colleagues from material science and engineering as well.
Great. All right. Thanks.
Thank you very much.
And, best of luck for your part. You got this. I saw some people saying they were nervous. I was terrified. Channel the energy into
Absolutely.
You got this. Okay. Bye.
As Maisie signs off on that lovely note, just think in 3 years' time, you could be presenting these webinars. That is how quick the time comes around. So lots of our undergraduates were themselves in this course not very long ago at all. And let's see if we have got Eugenia with us. Eugenia, are you ready to present your solutions for the evening?
Yeah, of course, of course.
Amazing.
Yeah,
Thank you so much for your work behind the scenes. It's been great. We've been able to do it together, haven't we?
Yeah. So let's share my screen first, I guess. So there's a quick short introduction. So hi everyone, I'm Ija. I'm a second year student at Somerville. So you're very welcome to come to Oxford and grab a coffee maybe and have a chat with me.
That's so lovely. I'm sorry, Ija, I pronounced your name slightly incorrectly as well.
No, that's fine. That's totally fine. It's quite difficult to pronounce, to be honest. Can everyone see my screen?
Yeah, I think we're all good. I've got a weird double image of myself, so I'm going to switch off the camera.
Okay. So me and Macy decide to share same mirrors whiteboard, I guess. Okay. So my questions are less like algebra related. They're like short answer questions. So let's go with the question 4. So part A, explain why this makes the car heavier when reference to at least one of the Newton's law of motion. So this question is talking about the racing cars that have spoilers, which will make the air direct flow over the car upward. So let's draw a quick diagram about this. So we have a tiny little car. It has a spoiler. So the air will make the spoiler will make the air pushing upward. So when it comes to the Newton's law of motion, we'll think about Newton's 3, Newton's like third law of motion. So a quick reminder about what this is about. So it is for every action force, there will always be an equal, equal and opposite reaction force. Why my pen isn't always working? Reaction force, okay. So that is Newton's third law of motion. So for this case, we have an upward force given by the air. So always the air will, so we have an upward force. So the air will always give an downward force, which is the opposite and equal force, acting as the reaction force. Therefore, we have given the upward force to the air. So the air will give a downward force to the car, which makes the weight of the car, well, I would say increase. Wait, I can't write anything on board now. Just give me a second.
That's all right. You're explaining it beautifully as you go.
Okay. Oh, I think, oh, okay. That's better.
Has it just come back to life?
Yeah.
Yeah.
Increasing the weight of the car. That is because we have a downward force and we have the weight itself for the car. Well, I will note it as W, and it has a force maybe F. So the total seemingly weight is just simply F plus W. And since we have a larger normal reaction force, F plus W is just Rn, I'll note it as. So we have a larger, as a result. Whoa, is that again? Okay, so as a result, the friction between the car and the ground increases. So that is question part A. Quite simple. Let's come to question B. So we have a student suggested that it is a silly design feature. So as the heavier an object is, the slower will it go. What is the physics behind this argument? It is correct. So let's think about it. Why it will like consider it being heavier? That is because like I said before, the weight is increasing. But actually, we have two different way to modify the mass. The first one is inertial mass, and the second one is gravitational. Gravitational mass. So what is the inertial mass? Actually, you can consider it as being the mass itself. So it's basically their own mass. It doesn't change anymore. So doesn't change. But what about the that is gravitational mass. So what about the gravitational mass? Actually, it is the weight. So we have W equals mg, but now the W, I'll note it as W prime, is just its own weight plus the force exerted by the air, so that we have a larger gravitational mass actually than the inertial mass. Okay. So actually the wording of that student isn't correct. We have increased the downward force, hence the normal reaction. So the maximum friction between those, the car and the ground, is increasing. So but it won't come slower because we have F equals ma. The larger mass being, the larger the mass, actually it will. Oh, let's say that again. So if m is larger, actually it reflects the difficulty of changing its motion. But you know, if we want and certain like velocity, it will always come to that velocity due to that acceleration. So it won't go slower, but since we have a higher friction, it will effectively prevent the car from skidding. That is the point. Okay. So that is part B. What about part C? Assume that the downward force created from the spoilers is proportional to v squared, where v is the velocity of the car. If it is possible for a racing car of mass 800 kilograms to drive on the roof of a tunnel, provided, oh, be careful, it is the roof of the tunnel rather than the ground. So provided it is traveling faster than 150 mph, determine the value of the constant proportionality. Okay. So we have to analyze what is the force on the car now. So it is on the roof of that tunnel. So we have the downward gravity. And also, since we have a seemingly pushing downward force exerted by the air, that is pushing upward now because it is on the roof, obviously. So if we want that system to be equilibrium, we have F is alpha v squared. Since we assume the question said they are proportional to v squared, so I have a constant alpha here that is equal to the mass of that car times the small g, which is the weight of that car. So we have alpha being equal to mg over v squared. And here, know that the unit of the velocity is not meter per second, so we have to change it into that. So V is 150 mph, which is, note that we have 1 mph being equal to approximately 0.45 meter per second. So we have 150 mph being equal to 67.06 meters per second. Okay, so we plug those values in, and so alpha equals, our mass is 800 kilometers. Note that we have to also plug in the units. So that is G over 0.45. So the final answer is being 1.74 Newton meter squared. Oh, sorry, the second square per meter. Okay. Meter. Is there any question regarding question 4?
No, I think you're good. And what I've done as well, Ijaz, while you are just presenting your final question, if anyone wants to put answers and questions in the chat for Jack and for Helena, do feel free. They're going to start answering by text while you present.
Okay, cool. So shall we come to question 5? now?
Yeah, I think this is
Okay.
our last one, isn't it?
Actually, no, we have another one, question 6, but that will be quicker, I think.
Cool. Well,
Yeah.
if not, we can always stop because we're going to send out solutions anyway. So let's see how we get on.
Yeah. Cool.
Perfect. Thank you.
No worries. So that question is about more practical and real life related. In these 3 places, hurricane hardly happen. However, if they were to happen, would they likely rotate clockwise or anti-clockwise, or no preference? Okay. So when it's come to hurricane questions, I usually think about one thing, that is Coriolis effect. Coriolis effect. I think most of us have come across it during A-level study, so I'll just go through it quickly. So when air travels, that is the definition of Coriolis effects, I guess. So when air travels in Earth, we have a force that is obviously Coriolis force. Okay, so what exactly is Coriolis force? It is an apparent force. So it is quite like imaginary, not real apparent force. Just like the centripetal force. So that is because of, due to the rotation of Earth. So that is the Coriolis force. Okay, so how does it do with anything about hurricane? So if we have a like an aeroplane in the northern hemisphere, so if we put it into the air, due to Coriolis force, since the Earth is like rotating itself, so it will tilt around, not like fly in the straight direction. So the question is, would it likely to rotate clockwise or anti-clockwise, or no preference? So the actual answer is anti-clockwise. The reason for this is that since these three places are in the northern hemisphere, the Coriolis force will let the air to rotate in toward rightwards. Obviously, if we are in the southern hemisphere, it is exactly the opposite. So it is like the leftward for, I'll write it down, for southern hemisphere. Will rotate leftward. And also, why does hurricane happens? That is because we have a pressure difference. That is, air tends to flow from the high pressure place or region to the low pressure region. Therefore, there is airflow and there is a hurricane. So in the northern hemisphere, we have it flowing backward. I'll write a diagram down. So if my air is from the south to the north, like this direction, then due to the Coriolis force, it will tilt and bend rightward, similar to those from the east to the west. So it will always tilt to the rightward. And therefore, what we get is anti-clockwise stuff. So the hurricane will rotate anti-clockwise. Does that make sense? Or is there any questions?
No, that's absolutely lovely. Thank you so much, Ija. I think just because we're starting to run a little bit short on time, what I'm going to do is I'm going to share the solutions for question 6 so that we've got the video of you doing 4 and 5, which is much better than the written solution. So thank you for coming on to do those 2 for us. It makes such a difference. If anyone does have any questions about question 6, because we don't have time for Ija to present it in person, drop us an email and we can take you through that. But genuinely, thank you so much. It was lovely to see you. I really love the way that you present. You're so calm. It's absolutely lovely.
Thank you so
and I'm
much.
sure everyone will also agree with that. You are a delightful, calm, pat presence for everyone here. It is delightful. Thank you. Thank you again to Maisie, who has been in the background. So she's just switched places with Ija and she's been answering the questions as they came up. Our 2 undergraduates are now going to leave. I'm very excited. I get to see them again in a couple of weeks. So I will see my lovely undergraduates. Once everyone sort of thank yous have passed, because I love to give everyone their chance to see all of their thank yous, I am going to share a direct link to the solutions now so that you don't need to wait. And then I'm going to briefly ask Jack and Helena, who are already answering questions in the background, to come on and just say hello to you. So I think thank yous have slowed down. Solutions are now in the chat, and Ija is a physicist at Somerville. So it's lovely to see her. And Jack and Helena, would you like to introduce yourself and say hello to us? Hey everyone, these are my colleagues. These are our engineering science and materials science behind the scenes.
Hey everyone, sorry, slight delay there. Busy typing away, and the brain can only do one thing at once, either listening or typing.
Not at all. That's why I'm giving you both quite a healthy lead in so that you can figure out where you are.
Appreciate that. So yeah, thank you so much for having us tonight, Kat, and hello to everybody on the call tonight. I appreciate it's late in the evening, but it's great that you're all here, super keen about doing well in the PAT. Hopefully there's a lot of budding material scientists on the call as well. But my name is Helena. I am the Material Science Access and Outreach Manager. So I am sort of the equivalent of Kat, but in material science. And a little bit about myself before this, I was also a student here at Oxford. I did physics at Oxford before I then joined materials. So I have been where you have sat. I have taken the PAT. I have survived through the whole process. And now I'm sort of on the other side of it. So I'm happy to answer any questions that you have, especially if it relates to material science.
Hi everyone. Basically the same thing, but I'm Jack and I'm at engineering science. So similarly, I am the access and alumni manager. Slightly different job, but I'm the access manager. And yeah, it's really nice to see you all and hear from you all. And any engineering questions, please fire them my way.
Lovely. Thank you so much, both of you. I'm going to start with a question that I think all three of us should answer because I know how often we get answered it, which is how much an advantage do you have if you do 4 A levels and or 3 A levels plus an EPQ? And you can see straight away all three of us going, Jack, you're still on screen. Would you like to talk about this for engineering?
Yeah, this is a really interesting question. I mean, I asked it all the time, and there isn't really like a blanket answer we can give. It is helpful to have a 4 level. Like it proves to us that you are capable of handling a higher workload and you manage your time well and all these things. So if you're comfortable and happy that you can do 4 A levels, all 3 in an EPQ, or whatever the extra thing is that you're thinking of doing, and still get the predicted, like the minimum requirement grades in the subjects that we ask for specific grades in, then do 4 and do an EPQ if the EPQ is relevant to the subject you're applying for. But be really kind of honest and truthful with yourself about how much work you can handle, and if there's any chance that doing the 4th A level or the EPQ might kind of suck academic energy out of the maths and the physics grades that you need, then don't do it. Because if you drop down to, say a B in maths or a B in physics, then it doesn't matter how good your EPQ is, we can't take you onto the course. So that's kind of the answer, really. So it massively depends on who's asking the question, really.
Thank you, Jack. Helena, let's hear your version of it.
I mean, I have nothing to add, to be quite honest. That's exactly pretty much word for word the advice that I also give students. So it really is down to you. And just like Jack said, if you can handle the workload of the 4 A levels and still hit those predicted grades, then we would strongly encourage you to carry on doing those 4 A levels, especially if they're all in the relevant recommended subjects, because that can be incredibly helpful to you once you're on the course. However, if it is going to detract from your ability to get the predicted grades, to get the offer, then I'd have a serious think about, maybe dropping one, focusing on the others to make sure you get the grades. And I will just add about EPQs. So I don't know if it's different for physics and engineering, but certainly for us in materials, we wouldn't make you an offer based on the EPQ. But that can be really helpful for things like your personal statement. And I've seen people asking in the Q&A, and I've been trying to type away whilst also listening, asking about personal statements and can they come up in interviews? Do they form part of the decisions process? For materials, they absolutely do. And it is quite common for students to get questions about personal statements in our interviews. I know that's not the same across all subjects here at Oxford, but for materials, let's see, my cat is cleaning herself in the background. Someone else has spotted it in the chat. That's Maria. She says hello. Maria's being distracting now. But yes, so EPQs can be brilliant for personal statements and for us for talking about in interviews, but they wouldn't form a part of your formal offer. I will make sure Maria knows that you all think she's adorable.
Thank you so much, both of you. I'll just echo. So from the physics point of view, we make our offer based on those 3 A levels just as engineering and materials do. And actually, we don't pay any attention to that fourth one. So the advice for our fourth one is, if it makes you a better, happier physicist and makes you better able to problem solve, go for it. But it's not going to confer any material advantage to you. And that goes with pretty much any of the extra stuff that you do. I did think it was interesting, Helena, that you mentioned about what we ask in interviews. I think this might be a useful one for us to go background. In physics, we very rarely ask you anything except academic maths and physics questions. So you could be asked about your personal statement, but it's unlikely. Let's go back in the opposite order so we can keep watching your Maria behind you, Helena. What about in materials?
Yeah, I'm trying not to let her steal the show, but you know, she's just a star. Yeah, so as I was saying, in material science, it is quite common for students to get a question in one of their interviews. So you typically have 2 interviews. They're both with different tutors, both at different colleges. And it is quite common at the start of one of the interviews to get a few questions. They're supposed to ease you into it. They're supposed to be the easy questions because it's about something that you've written about and that hopefully you're fine to talk about. So bear that in mind when you're writing your personal statements. Don't lie. Make sure you're happy to talk about anything that you include. I'd say it's speaking to students who've done material science interviews in the last couple of years, it's probably about a 50-50 chance that you'd get asked a question about personal statements in the interview. So it is quite common. And that would potentially guide the topic of some of the more academic physics or maths, or even for us chemistry type questions that you might get. So that can sort of colour the interview a little bit. Other times it will be as is in physics, very much academic focused the whole way through, answering physics, maths. I did throw chemistry in there as well. There is a little bit more chemistry and material science than there is in physics or engineering, so we do like to test that knowledge a little bit in the interviews, but it will be material science related, and depending on whether you're offering A-level chemistry or not, because it's not an essential subject, we will know the level at which to pitch that chemistry. So if you're not doing A-level chemistry, you might get GCSE level chemistry questions, for example. But it's all in the realm of material science, and it should be about sort of problem solving, so applying the physics and the maths that you know to solve some material science based questions that you might not really have thought about before, or conversations that you might not have had about material science, material selection, that sort of thing. But that's typically what the material science interviews are like.
Thank you, Helena. Jack, I know you've been typing a couple of answers, so I thought I would give you this courtesy 5 seconds to come back as well. What about in engineering? Have you got anything relevant to say about how you feel about personal statements in engineering?
No, pretty much exactly the same, to be honest. They do sometimes come up, not all the time. I think sort of anecdotally, talking to tutors and students, I think they're used either if, well, most commonly used if the tutor thinks you're a bit stressed and a bit nervous and you're a bit out of sorts. They might feed you a question about your personal statement because it should be something you're comfortable with, and it should kind of ease you into the process because you should know about your personal statement. Or they're trying to fill the end. They kind of made a decision, they're happy with how things have gone, and they just want to kind of round stuff out a bit. So the best thing to do is just know your personal statement as well as you can, and don't, as Helen said, make sure you're honest with everything you put in there. It might come up, it might not, but if it does, it should be something you're pretty happy to talk about. So it's actually quite a good thing if it comes up.
I love that as a final statement, Jack, because in physics we almost never ask. So full disclosure, we're not like you guys. We'll just about remember to ask you your name and check that you're the right person. Otherwise, we're straight in with the maths and the physics. But if we were to ask you something, it's not to trip you up. It's because you've written something that we're interested about and that we want to know about. So yeah, you should be happy with it. We've got a few questions about interview dates, and I think all 3 of us are pretty similar for this, aren't we? As in, it's quite late when you find out about interview because we've got a lot of material to go through. So it can be quite short notice, be prepared for that. But also, we're used to seeing you at school. So please don't feel that you need to have taken a day off school. We're quite used to seeing you in a corner of someone's classroom. That's where most people do their interviews. So, yeah, happy thumbs up from Jack and Helen. I can just take that one. Now, we've had an interesting one here, and I think this might be a nice chance for us to talk about colleges and how we centralise admissions. Because somebody has asked, do colleges have a limit on how many offers they can make to students from the same school? Will our chances of getting in be lower if multiple people apply to the same college? And my point of view from physics is, I honestly don't even know if we would notice. So we are very centralised in physics. We make sure that we share things out to make sure that every college interviews roughly the same number of people per place. How about you two? How do you centralise your admissions for your engineering? Just because you're still on screen, Jack, so you can go first this time.
Oh no, I was trying to think of my answer. I don't think we know is the answer as well. This is a question that this is a lot that I'm not certain, but I am pretty sure that the tutors don't know what school you're at, unless it says it somewhere in the statement they've got and read. So I wouldn't worry too much about that. And I certainly wouldn't be picking and choosing colleges based on where the colleges your friends from school have decided to apply to. I've never heard of a rule that says a college can only have X amount of people from a certain school. But just through the sort of nature of people applying to different colleges because that's where they feel comfortable, and people being reassigned to different colleges based on the number of spaces at colleges and different subjects, it's pretty rare. I can't imagine that you'd get more than 2 or 3. That's quite high, I would say, for one school to have at one college in a year. So it's pretty unlikely that if 5 of you all apply to the same college, you're all going to end up there anyway.
Yeah, I guess just to add on to that about materials, like I think tutors can see your school. I think it's part of the UCAS application, but honestly, they do not care. They will not look at that. It's available for them to see, but they won't look at it because they're not at that point interested in what school you're from. They're interested in your academic ability and how well you do in interviews and the rest of your application. And as with engineering and physics, our decisions are also made centrally and quite literally because we are such a small course. All of our tutors sit in the same room together, like in a physical room, around a boardroom. I'm in the room as well, so I get to hear what happens.
We sometimes do. It's just a really big room.
Yeah. Yeah, so it works a little bit better when you've only got about 15 people, but rather than, I don't know, the 50 or so for physics, probably. I don't know. But yeah, they're literally all sat around a table in the same room, discussing the candidates and sort of reassigning colleges as well, as Jack was mentioning. If one college is particularly oversubscribed with fantastic applicants that year, you will get a place at a college. It just might not be your first choice college. It might not even be one that you've had an interview with as well. So it's always worth saying. So picking up on the point mentioned before, if you did try and apply to the same college as all your mates, thinking you'll get in and you'll know people, chances are you'll end up at a different college anyway, even if you all applied to the same one. So there is that sort of reallocation process, and it is, again, very centralized. All the tutors talk to each other, and there's certainly no quotas based on what school you're at. That's not a thing. They don't care at that point. So hopefully that's reassuring.
Very reassuring. And now I think we've got, not that the others haven't been serious, but so far we've been on the easy stuff for us to answer. We've now had a few questions about different schools. So if you go to a particular type of school, if you go to a state school or a private school, how are you going to be viewed? And while you always get the chance to compose your answers. I'm the host, so I have to go first and give you the thinking time. But I would straight away say no. So for a start, we will look at statistics around your school. For example, how many people get particular grades, how many people are on free school meals. We don't actually directly look at what type of school you are at. And so from either side of this, it doesn't go any differently. So it's not going to influence our decision positively or negatively in either way in physics. I'll now get you two. You've had your chance to come up with a slightly more coherent answer, which will hopefully help mine. And then we'll circle back round and I'll talk about the R score for physics. Just because I've just been asked, not because I fancy it.
Who wants to go first? Do you want to go first, Helena?
I know, I can go first. I just want to say I'm intrigued by this R score. I'm curious what that is. But yeah, basically the same as Cat. So the only way that the type of school that you were at is used is that sort of contextual information, which essentially puts your achievement in the context of everyone else at your school. That's the limit of really at this point what we use your school type for. Obviously, if specific things are mentioned in things like your teacher reference, for example, something that's happened at the school has disrupted your education, sort of mitigating circumstances, then we would take things like that into account on a case-by-case basis. But that would have to be specifically mentioned in the references as something that's happened. Like, I know sometimes schools get put in special measures, for example. That might be something that gets mentioned, and that would play a part in the decision-making exercise because that's impacted your education. But as Kat said, the only way we use the school type is to add a bit of context to your application at this point. There's no quotas, there's no sort of deciding factors to do with school type whatsoever. Dispelling those rumors right here, right now.
I've also just put the link to the contextual data that we do take in the chat. So if anyone wants to look that up, you can have a look. Jack, you've had loads of time to have a good think.
Yeah, I mean, I'm trying not to go overboard because whenever I answer this question, especially like in person at UCAS fairs and stuff, I've got a whole spiel that I go on for ages about it, but it has all been covered basically. So I think exactly as been said, it's just about that context. Like not all schools are born equal, and that's kind of where the point of this is. There are some schools where every single person who goes there, regardless of how able, passionate, invested they are, they will just get 9 9s at GCSE and 4 A stars at A level. They just will. And if they all get that, does it prove that anybody there is good, really? Do you know what I mean? It's that like flexibility. And there are some schools where no one ever gets that. And then one year you might have one person who gets 4 A stars at A level. And that is like no one's ever got that score ever in that school, ever. And it's they're the top 0.3% of students to ever graduate from that school. Is it fair that objectively on paper, that second person at that second school is at the same level as all the people at that first school? That's kind of where this comes into play. So basically, as long as you do well for your school, that's it. That's all you need to worry about. And for our subjects, there's not a huge there's not much headroom to kind of play with anyway. So realistically, all this does is play with how you've done academically, right? So you have to get the minimum, but the minimum and the theoretically possible you could get, the highest possible you could get, that gap is tiny. So it doesn't make any difference really at this point. Just do as well as you can, and that's it.
Thank you. That was a lovely way of putting it, sorry. And I think this brings us, so somebody's asked about the R score, which you will find on our physics website. So our R score is a combination of your PAT mark and 10 times your contextual GCSE score. Okay. Now, to be really clear, our contextual GCSE, as Jack said, what it lets us do is spot people who have done unusually well. So it lets us see how you've done in your GCSEs compared to other people. We never assign a negative contextual GCSE score. So if, for example, you were at one of these schools where lots of people have fantastic grades and you didn't, we would never use that against you. We use our contextual GCSE score and we multiply it and add it to your PAT score just to identify people who we maybe should have another look at. So we're only ever using it to identify people who have done unusually well. And in terms of the actual extent to which we look at GCSEs, we have so much information about you at Oxford. We are incredibly lucky. Not only do we have all the information that other universities have, but we have your admissions test score, and then we interview you and we get to meet you and we get to find you. So it's a small part of the information about you, but it's not a massive deal breaker. So don't worry if you've got a couple of dodgy grades in there. It is not the end of the world. Don't worry if you have 14 grade 9s, that's lovely for you, but it doesn't guarantee you a place. So it works in both directions. Anyone, and there are now a raft of versions of this, if we don't have this information, we just don't use it. So you just get a neutral score and then we look at everything else we've got about you. So if you didn't sit GCSEs, as lots of our applicants don't, because actually only people in a very small part of the world sit this particular set of exams, even as we go wider up to Scotland and into Ireland, we're already at different qualifications. So if we don't have it, we just don't use it. And we won't use that against you. Hopefully that has helped. Jack and Helena, is there anything else you'd like to add about those kind of points about GCSEs and things?
Not really from my side. I think that sums everything up. I don't know if there's anything else you want to add, Jack?
No, not really. I think, yeah, you covered everything. There is one thing I'm just going to steal this question because I've seen it and I can actually answer it for the first time. I've never known this, and then I found out the other week and I know the answer. It's a question about engineering. Sorry, to be specific for a second. So if you go on UCAS and you look at engineering at Oxford, you do get a general engineering degree that you can apply for, and you also have like specific engineering courses. So biomedical, mechanical, all those. What is a bit rogue and a bit weird, and I don't think people necessarily know, is that no matter which of those courses you apply to, you go onto the same application stream, you come to Oxford for engineering if you get offered a place, and you do the general engineering degree. It makes absolutely no difference which one of those engineering degrees on UCAS you apply for. Somebody told me it was to do with the fact that people don't necessarily know that you can specialise if you come to Oxford later on. So we added in UCAS codes to kind of let people understand that. But it makes no difference at all. So just apply for any of them. But I mean, I'd say apply for the general one because that's the course you're going to go on to anyway. But it honestly makes absolutely no difference. And I think it's probably like the best way we can do it, where we can kind of half show you that you do general engineering, but you will end up getting a specialism. It's weird, but that's just the way it is.
I'm so glad you answered that, because the physics building is right next door to engineering, and the most popular question I get asked at open day is, should I apply to physics or engineering? And I'm always like, I don't know. What feels good to you? Like, you make your choices. And I've never been able to answer anything about the UCAS forms. Thank you. That is incredibly useful. I'm just having a flick now to see what else. Oh, I'm going to answer one, even though I probably don't need to, which is, of course, we're happy to use Scottish Highers and Scottish Advanced Highers. Obviously, I'm going to be biased. We accept people from all over the world, and these qualifications are not unusual to us. So again, we might not be able to put it directly into our formula, but that is the case for quite a lot of our candidates. So we just look at all of your other information, and it's never a case of computer says no. If either of you two have a particular qualification you feel strongly about and want to pick here and talk about it, do go for it.
No, that's a good summary. I will say, if you do want to just find all the details about other qualifications are available. It's all available on the website. I don't know if Kat, are you typing away to find the website by any chance?
I was not, sorry, I was answering something else.
That's
I forgot to mute myself so that I didn't get my clacking on the keys.
I can drop a link in the chat because there's a web. Oh, Maria's on the move again. Enjoy the show. There's a link that I always use to just double check whenever anyone has any international qualifications. There's full details on the university website, so you can see sort of the equivalents in any qualifications, whether they're accepted, what the grades are equivalent to, what the subjects are equivalent to. So do just have a check on there, and you'll be able to sort of translate it roughly to what we're talking about with A-levels. Yeah. I think there is one question that I've seen that I would like to pick up on a little bit. I don't know if you guys want to as well. Talking about, someone's asked, apart from the maths and physics, do the other subjects that make up the entry requirements matter? And I think this is always a really interesting discussion between the three of us, because we have sort of different subjects that we prefer outside of the maths and physics. Yeah, I'm getting a thumbs up from Kat, so I'm going to run with this one. So yeah, as you probably noticed, for materials physics and engineering, the two essential subjects for all three of our subjects are maths and physics. However, the next tier down, the sort of third recommended subject for these two, it's further maths. For us, it's chemistry. So what that basically means is, if you have the choice for your third subject, those are the ones that we would prefer. So in materials, we would prefer that you studied chemistry, and for the others, further maths, I believe. Please correct me if that's outdated information, but I believe it's still further maths for both engineering and physics. Then the next tier down, what we call helpful subjects, for us, that's where further maths comes in. And it's basically to do with what's going to be most helpful to you when you're on the course here at Oxford. So for us in material science, it is very physicsy. You've got to know your maths, but there's also a significant amount of chemistry in there. So doing a chemistry A-level is more helpful to you for our course than doing further maths is. Obviously, for general math skills, the more maths you do, the better. I think we all agree on that. But for us, it's more beneficial for you to have done some chemistry. Now, the way that those sort of recommended and helpful subject descriptors come into play is, well, they're not essential subjects. You don't need to be taking those. However, they can be useful. If you're not taking those subjects, we do recommend doing a little bit of self-study, perhaps, or taking them to an AS level if you can, because that will help you on the course. For us, if you're not taking chemistry and you apply, as long as you're taking the maths and physics, that's fine. That's sufficient. But we would expect you to still know your GCSE chemistry, as I was mentioning when we were talking about interviews. So the fact that you're not studying the recommended or helpful subjects alone is not going to be the reason that you don't get an offer, because they're not the essential subjects. So that's sort of how I explain at almost 8:30 on a Wednesday night what the difference is between the essential, recommended, and sort of helpful subjects. I hope that was clear.
I think
Jack, you
Helena
wanted to-
does herself down. If you have any idea how many Wednesday evenings Helena and I spend together over the course of the average year, everyone. We're all pretty good. We've got quite a few about these kind of things, so I am going to answer as well. So really similar to Helena. We want maths and physics. Those are our two required subjects. And that can be at advanced higher, at A-level, as your higher tier international baccalaureate, as your advanced placement courses. Whatever you're taking, we want maths and physics. We would then really like further maths. But if you don't have it, that's okay. We're interested in your ability to study maths at that level. There are lots of reasons why people don't have further maths. Sometimes your school doesn't offer it. Sometimes you didn't realise at 16 as you sat your GCSEs that you would like to take further maths. Sometimes you did something else. All of these are absolutely fine. And whatever subjects you offer, as long as you've got maths and physics, we just want to know that you are capable of studying further maths. You don't actually need to be studying further maths. If, however, you don't have further maths because you think it's too hard and too mathsy, I will freely admit this might not be the course for you. Even if you're not studying further maths, you should harbour a deep love for further maths. Otherwise, it's not going to be fun. And as for third A level, somebody's asked, which actually made me a bit sad, would doing a third subject in a humanity be disadvantageous? No! Do whatever makes you happy. It's a bit like the EPQ. If it makes you a better person and a happier person, absolutely go for it. Jack, how do engineering feel about further maths?
Oh, I've done something weird to my screen. Hold on, I can still see.
No,
Right.
I can see you. We're okay.
Yeah, no, everything's really weird and big, but it's all good. It's all good. It's helpful. It's the same as you, really, in that it is helpful to have. You don't need it. Lots of our students come here having not done it because not all six ones offer it. If you are choosing not to do it because you don't like maths that much, then same
Yeah,
thing.
just a bad idea.
Probably not there is a lot of maths on these courses, right? That's just the fact of life. The maths you do, certainly for engineering in the first year, is pretty much a further maths A level anyway. So the idea is everyone's kind of got the same benchmark of maths before you progress further down the course. So it's helpful to have it. You don't need it if you don't want it. If you'd rather do a different subject, that's fine, as long as you still do well in your conventional maths A level. But yeah, if you're in a position where you're thinking, do I do further maths or not, and you don't want to do further maths because you don't like maths that much, then have that honest conversation with yourself about whether you think this is the right course for you, because they are maths heavy, right? There's no getting around that.
And just to echo that sentiment as well, for us with chemistry being the recommended subject, if the reason why you haven't taken chemistry as your third A level is because you hate chemistry, have a think about whether you actually want to do material science versus maybe physics or engineering instead. Because there is an element of chemistry within materials. Not a huge emphasis in our course, but it's there. So if you hate chemistry, there's going to be significant chunks of the material science course that you're just not going to enjoy. So yeah, I'll echo that sentiment there as well.
Yeah, I think Jack and I are very strong on this. Be like, you should definitely enjoy maths. It's a good start. I think in physics we're even stronger than engineering science. It's not further maths in the course of the first year. It's further maths in the course of about the first 4 weeks for us.
I remember that.
It's quite a rapid
Yeah.
bringing you up to speed if you don't have it.
And it's also worth saying, actually, even if you have done further maths, so I did further maths, but there were certain modules within further maths that I hadn't done, that
Yeah.
a lot of my peers had. So I had a crash course in, I think it was like Further Pure 3 or whatever. See, I still remember this from all those years ago.
Burned in.
Even though I'd done further maths, I was still learning new stuff as if I hadn't done further maths. So there's a whole point of that first term, year, 4 weeks, whatever it is to get everyone onto the same page, no matter what their third or fourth or whatever A levels were. So getting everyone that same foundation, whether you've done further maths or not, whether you've done chemistry or not, that's the crucial part of those first few weeks. So I always like to add
Amazing.
my little story there.
No, it's really helpful. Thank you. We have got 2 minutes left. So what I think is we'll all type up a little bit while the other person is talking. But let's think any last minute hints and tips or general thoughts, a bit like old school Jerry Springer, our last thoughts for the Pat before we hand over. Would you like me to go first so that you two get the more polished version again? Yeah. It always feels a bit unfair, but it is my course. So what I would say, everyone, is we really hope that by taking part in these courses and by doing the PAT, wherever your physical sciences journey lands you, it's been beneficial. So the work you have done getting to this point is going to help you be better physicists, better engineers, better material science at any university. If you then get as far as interviewing us with us, hopefully you'll find that beneficial too. And if we see you in a couple of years' time and you are one of our undergraduates, A, that will be absolutely delightful, but B, we hope this helped get you there. But have faith in yourself and remember that it is worth it regardless of the outcome. I've done mine. One of you two can go next.
I can jump in as someone who, like I say, lived through all of this sort of, how I don't want to think about many years ago, about 13 years ago now. Gosh, time flies. The best things you can do at this stage, to just anything that's going to help you feel more prepared. So we know that the PAT's coming up in a few weeks' time. You've done a lot of preparation already if you've been a part of this course. I never had that opportunity, so you're already, making the most of the opportunities that you've had. Keep practicing. I would say keep doing the sorts of problems that you've been working on through this course. Keep looking at past papers. Keep doing things like Olympiad papers, Isaac Physics. We love Isaac Physics here. Just keep practicing. Because like Kat said, not only would that help you with our application process, whether it's for the admissions test or for interviews, it'll just help you be a better scientist and it'll help you feel more comfortable with those scientific skills. So that's my one little piece of advice. Just keep practicing. You don't need to over prepare for things like interviews, but do whatever level of preparation helps you feel more comfortable, because then you'll feel more confident. Your brain will be able to think better. Drink water, stay hydrated, get a good night's sleep, all those general advice and tips as well. But yeah, just keep practicing and you'll all do the best that you can do, and that's as much as you can do. So yeah, best of luck to you all.
Yeah, basically, I'd say exactly the same thing. I think one bit of advice I will throw out, which is a bit rogue and might raise eyebrows, I think, but I think is just to remember that it doesn't matter if you don't get in, right? You're probably applying for 4 other really good universities for the subject you're interested in. So just go into it like aspirationally, hopefully, it'll be great if I'll go, but if I don't go to Oxford, I'm still going to go to another great university. Like, I think people get very worked up in their interview, like, oh, I really need to do, but it honestly, in the grand scheme of things, in the wider life, it's not the end of the world if you don't get in. And if you just kind of bear that in mind when you go in, you will do better in your interview and arguably at the pat because you're a bit more chilled out about the whole thing. So just try and be as relaxed as possible. And I know it's easy to say, but that is the best thing you can do is just try and be as chill and comfortable. Obviously, do practice. I should just say, don't just rely on being chill as your like key to getting in. But yeah, practice the past papers, practice talking to people. You know, it's something that isn't that widely sort of talked about, but talking to friends, talking to family, getting them to kind of probe you on your ability to talk about bits of physics or engineering or computer science that you're interested in is really, really useful. And it should be fun, really, because you should all enjoy the subject you're applying for.
Thank you so much, Jack. That was a lovely last mention. We do all love the course that we're applying for, and that is absolutely what we should remember. Everyone, thank you so much. Your PAT is on the 22nd or the 23rd of October. Enjoy the last couple of weeks of preparation. Get stuck into everything that you can. Feel free to drop any of the three of us emails if you have any questions. I'll send the recording over tomorrow. But for now, goodbye and good luck.
Maria says goodbye as well. I'll let you see the cat as we're all leaving.
We should always let a cat have the last word of the preparing for the pat. We should make this an annual tradition.
You've got to pay the cat tax. If they can be seen in the background, there you go.
This is completely irrelevant. It's now just the three of us talking, but can you imagine if I brought one of my chickens?
Oh, the best. That would be so fun. There you go. Just, Maria wishes you luck. Think of Maria. Keep calm. You'll do great.
Thank you, everyone. I'm going to switch our cameras off now and stop the recording. Bye, everyone.
Bye.